Okay, but before we do the main part of the lesson, I want to do a quick review of implicit differentiation. Now, when we usually would do implicit differentiation, I would give you problems like x squared plus y squared equals 25. And then I would say, oh, find d dx of both sides, right? Do you remember these?
Oh, yeah.
Yeah. So we've already did. So quick review. So if we do d dx of x squared, that would just be 2x. But when we come across y squared, that would be 2y dy dt. And then a constant would still just be 0, right?
Yeah, y t.
Oh, sorry. Dx. Well, we're going to be doing d. There we go. Okay, so the goal with this lesson is going to be somewhat similar, but instead of d dx, we are going to take d dt, which means this is so it's the rate of change with respect to time.
We literally just did this.
Okay. So rate of change with respect to time. So this is really the heart of calculus, because calculus takes a look at how things change in terms of time. So it could be area, it could be volume, it could be a linear measure. So here I have some formulas where I just want you to take d dt of both sides. Yes.
So is it just going to be d dx, but with a different variable, essentially, instead of like x?
Exactly. So I'm going to take d dt of both sides. Now, when we did implicit differentiation previously, we had something in terms of x. So when we did d dx, right, we were able to differentiate normally, so to speak. Now, we're never going to have a t in our equation. We're always going to have different variables. So when we take d dt of c, that's just dc dt. Well, you need to know how to do this before we lead into the other stuff. Okay. All right. What happens when? Well, what's 2 pi? 2 pi is just a coefficient, so it's just going to be 2 pi dr dt. That's it.
Wait,
right?
Why do you put dr dt?
Well, if I take the derivative of 2 pi r, that would be 2 pi times dr dt. Because you can't get rid of any of these variables at all. Because it's with respect to t. So it's kind of like, oh, what's the derivative of c? That would be 1 dc dt, right? This would be 2 pi dr dt. Okay, now let's take a look at the next one. So if I take d dt of both sides. Okay, on the left side.
That's all you do?
Mm-hmm. You need to be able to do this first before we can actually apply it. And notice these formulas are all formulas that should look familiar, right? This is circumference. Next one is area of a triangle. Okay, so d dt. So this is basically going to look at how does, let's say we have the area of a triangle, how does the area of the triangle change with respect to its other dimensions? Now, this is going to be a u times v situation. Okay, so shall we make, we can make 1/2 b u? Okay. All right, derivative of 1/2 b will be 1/2 db dt times h.
0, the derivative of h.
Well, h is not a constant, so
Plus
1/2 b times dh dt. So now we have u is 1/2 b times the derivative of h with respect to t, which is dh dt. That whole thing, that's our answer.
Oh, that's ugly.
But what the goal, okay, it's not that ugly, but the goal in this lesson is we're going to be able to plug all those values back in and actually solve for one of those missing components.
So, this equation assumes we find it.
This is just to have practice with taking the derivative with respect to t of both sides.
It's just like
Okay.
starting point.
Yeah. So here, let's try the next one. d dt of v. d dt, oh, this says pi r squared, where h is equal to 4. So that'll be 4 pi r squared. Right, so I'm going to kind of plug in.
Oh, wait, never mind.
Oh, we haven't done the derivative yet. So if I know one of my values, I can plug that in before finding the derivative. So on the left side, I'll have dv dt. Now on the right side, I don't have to worry about doing a product rule or anything because
Is pi like x?
4 and pi are that's just a coefficient.
Is pi like x?
Well, it's not a variable though, it's a constant.
So it's 8 pi dr dt.
It'll
It's
be
like a
8
number.
pi r,
Oh.
8 pi r dr dt, right?
Wouldn't it be
Okay, so the 2 goes to the front, right? So 2 times 4 pi would be 8 pi r to the first. Remember, we still have to apply that power rule. So r squared becomes r to the first times dr dt.
Why is it dr?
Well, these are, if you notice a pattern, they're all multiplied. Like this one had an r, so you had a dr dt. This one had an a, so it's dA dt. This one had a b, dB dt. This one had an h, dH dt. Let's try one more, and then we'll do some applications. Okay, on the left side, so d dt of y is just dy dt. Secant squared theta. D theta dt.
Oh, so you have a theta in there? But don't we find...
Well, theta is now our variable here. So it's, remember, implicit differentiation is like derivative of the outside, keep the inside the same, times derivative of the inside. So derivative of the outside, secant squared. The inside is our theta, times the derivative of theta. All right. Okay, here we have a right circular cone. Volume is 1/3 pi r squared times the height. What would we do if r is a constant? Okay.
Does anybody have lotion? Really?
Oh my god, you don't want that. No, you're killing that.
Jerry. It's vanilla. Ooh, I have some.
You just throw it.
Can I borrow some too? Yeah.
Sorry, I just
Everyone have some lotion.
just like pass it around with smells good.
Okay. Great. Left side is going to just be dv dt. Now, I want to see how dv dt, so the change in volume with respect to time, is related to dH dt if r is a constant.
1/3 r squared.
So this whole thing, 1/3 pi r squared, is all one constant.
2/3 pi r.
Oh, you have to use right?
No, you don't need this whole
2/3
thing.
pi r.
That's
2/3 pi r.
It's 1/3 pi r squared dH dt.
Oh, I was doing
Because-
the other one first.
Listen, r squared is a constant. So if r squared is a constant, that makes 1/3 pi r squared one whole big coefficient.
It does. Totally does.
It's saying
it
here.
would be
How is this? So here's what we're basically doing. We're going to take turns with what this would look like if the radius was constant. Now what if the height was constant?
So it's just basically what the question's asking.
So now what would the
So
difference?
1/3 pi
It's just
r.
Yeah, so this time,
Wait, wouldn't it be like b times u though? I mean u times.
okay, here. Let's say I want to rearrange this. So 1/3 pi h would be constant times r squared. So now this time, that whole piece is a coefficient. It's constant, it's not changing. So dv dt,
Equals 2/3 pi.
2/3 pi h r dr dt.
Pi HR.
Well, yeah, because you still have an r to the first power if we use the power rule. So the 2 goes to the front. Nothing else here changes. R to the first power times dr dt.
Okay, now
Okay.
do that.
Okay, now neither one is going to be constant. So now we have to do u times v.
How do you know to change like the equation like that?
It says it.
No, like how do you change it?
So all I did, if h is
What does that
constant,
mean? H is constant. Like how do you know what to do?
like it's a number. Like it could be 10. I don't know what it is, but we treat it as a constant.
Like we treat it like pi.
Listen,
Like why'd you write it? Why'd you write the equation differently?
okay, if you go back to like 10x squared, 10 is a constant. Yeah?
Yeah.
So if I do the derivative of this, this would be 20x. But now, yeah, let's say it's y equals w times x squared. Now all of a sudden, I have to do a u times v situation because I have this is variable and this is variable. But what I'm saying here is h is just some number. We don't know what it is. So we would do the derivative treating that like as if it were just a regular number.
You're basically saying like H could be 3.
So basically, we treat it like how we would treat a pi, right?
We treat it like a pie. Okay, this one.
Hey, that's not what I was asking. Why do you write the equation differently? Well, you can always do.
Oh, you don't have to write the equation differently. I just rearranged it to put the h with the 1/3 pi because 1/3 in pi is already a constant.
It's just multiplication. You can rewrite
I just-
multiplication.
I just moved the h, like this one, the h was here. I just rewrote it because I just put the r squared last because we were treating r as a variable. Okay. Now we'll do u times v. So maybe I'll make this whole thing here u and this v. Does that?
Yeah.
Now, one other thing, we could always move the 1/3 pi all the way out to the front because it's just a coefficient. But since we're doing this, I'll just leave it. Okay, so what would u prime be? It would be 2/3 pi
r dr dt.
dr dt times h
plus 1/3 pi r squared dh dt.
plus 1/3 pi r squared dh dt. Good.
So why is the r squared on the u?
No, that's
Wait.
ugly.
It's not R squared.
Yeah, sorry.
I don't like that.
Sorry.
It's ugly.
Is it worth simplifying this into parentheses?
take out should we take out like 1/3?
1 pi
R, yeah.
I probably would if we actually had to plug something in.
So it would just be 2R.
And yeah, you could take out a 1/3 pi, and that would be 2r.
Pi r.
Yeah.
Could do like a
Yeah.
1/3 pi
And
r.
so on.
It's the type of thing that makes me
Okay. Okay, the base of a right triangle is increasing at the rate of 3 centimeters per second, while the height h is decreasing at the rate of 2 centimeters per second. All right, when b equals 4 centimeters and h equals 3, find the rates of change. Okay, so let me just write down first. I'm just going to draw like a right triangle here, okay? Again, what we're talking about are shapes that are changing with respect to time. So in this case, here's our height. Here's our base. The height, the base of the right triangle is increasing. So this here, so the base is increasing. That means that is dB dt is increasing. What's that?
How does the base increase?
It's getting bigger.
Stretching something. Oh,
So
okay.
here's what's happening. Like the shape is changing. Okay? So we have a triangle and the base is getting bigger and bigger at 3 centimeters per second. At the same time, the height is decreasing at the rate of 2 centimeters per second. So that is going that way. So dH dt is decreasing. So I'm going to put a negative in front. Negative 2 centimeters per second. So you can kind of see what's happening to our triangle. It's kind of flattening out, kind of, right? This one's going out this way. This one's going. So it's becoming kind of a squished triangle, right? So I want to find the rate of change of the area when b equals 4 and h equals 3. Okay, now those are not constant. Nothing is constant. So the first thing I want to do is what would be the area of this triangle? Okay, area is 1/2 base times height. So kind of like what I gave you on the previous page. There's nothing that is constant here. Sometimes we have a constant and we would plug that in, but we don't. So I want you to take d dt of both sides. Now, if you want, go ahead and leave 1/2 out in front. Just, you don't have to. You can leave it as 1/2 base times height. Just, okay, on the left side, what do we get? We get dA dt. What do we get on the inside? Okay, so the derivative of b dB dt times h plus b dH dt. Okay, now that we did all of that, now we can start plugging everything in. So I want to find dA dt. What did we say dB dt was? 3. Times height. What was the height given? 3. Plus the base, 4. And negative 2. So just a half? And then we just need units, so 1/2 square centimeter per second. So that just means if we took this triangle, right, and this is getting bigger at 3 centimeters per second, this is getting smaller at 2 centimeters per second, right at the instant when this is 4 and this is 3, the area is increasing at 1/2 square centimeter per second.
Oh, that's cute.
So it's still getting bigger. Now, would that necessarily be true at a different instant in time?
No.
No. Okay, so it's at that snapshot. How is the area changing if those two sides are changing at the same time? Okay. Now what about the length of the hypotenuse? So let's put a c squared there. So I know b squared plus h squared equals c squared. Again, everything's changing. The height's changing, the base is changing. Can the hypotenuse stay that, whatever the length? No. So we're going to treat that as a variable. And so I want to do d dt of both sides.
Well, you not treat it as x.
They're all treated as a variable.
You have to
So-
plug in
So we'll plug in the information at the end. So we have 2b dB dt plus
Isn't it h squared? Oh, no.
2h times dH dt equals 2c dc dt.
Cancel out the twos.
Sure. Makes it a little easier. All right. Now we're using the same measurements. So B was 4. dB dt was 3 plus the height, which was 3 times -2. Okay. I have too many variables. I've got a C and a dC dt. But can I figure out at the instant, so when the base was 4 and the height was 3,
3, 4, 5.
good. So we have 5.
So it's always gonna be something.
If you ever end up with too many variables at the end, it means there should be some information you can go back to substitute it. All right, so 12
12
minus 6,
6 equals 5 dC.
so 6/5 centimeters per second. So that means at that instant, the hypotenuse is increasing at the rate of 1.2 centimeters per second. Yes.
Why can't you just plug in from the beginning b squared plus a squared? Like, why do you take the derivative?
Well, because it's changing. The only time that you could plug in right from the beginning is if something's not changing. Like, I'll give you an example. I think we do. Do we do that on this one? Nope. I was trying to remember if I think you have one on homework. You have one on homework where there's like a ladder leaning up against the building. So let's say you have a house and there's a ladder here. So let's say the ladder's slipping away from the wall, right? So that means the top of the ladder's going down. But is the actual ladder changing? No. So I would be able to plug that measurement in. But what's happening in this case, all 3 things are changing at the same time. Okay. So you can only plug in what is constant from the very beginning. Okay, so like the perimeter is also changing. What would be the perimeter? It would be plus H plus C. Yeah, you can rename anything. If you want to do A plus B plus C, it doesn't matter to me. It's fine. Okay, so then d dt at both sides. Well, that's just going to be dB dt plus dH dt plus dC dt.
Centimeters per second.
Yeah, so we end up with, dB dt was 3 minus 2 plus 6/5. We found that out from the previous answer, so.
Centimeters per second. Because think about it. It's 6/5 centimeters per second. Like,
Yeah.
It's all rates.
So it's just 1 plus 6/5, or.
Like, look at dC over dt. And look at, like, the units of dC over dt.
Okay, no? Which one? Is it the units?
No, the units.
Oh, perimeter is just a linear measure. Same as like the length of the hypotenuse. Only area would be square and volume would be cube. Yeah. Okay. One more of these. Let's say the angle where theta is the angle where the base and the hypotenuse connect. Okay, so here again, here's our base, here's our height. We're talking about this angle. So as this base is going out, this is going down. What do you think is happening to the angle? Yeah, it looks like it's going to be getting smaller. So if it gets smaller, hopefully we get a negative rate. What's the relationship now between those 3 parts? Tangents. Okay, So you could use sine, cosine, or tangent because we found out what C would be. It doesn't matter. Use whatever. Generally, if we're working with these two sides, I would just use tangent.
Use what you're given.
Yeah, use what you're given, just in case, because if you make a mistake on the hypotenuse at some point, that would mess up your answers for this one.
Yeah.
Whereas if you use what you started with, you
But could that be also just error carried forward?
yeah,
And that-
but you would still lose a point for the answer. Like on the it's, I know. It's like there's some things that you can gain the point back, but you'll never get the answer point.
Okay.
Okay.
Yeah, I was like, because it kind of.
Oh, that was very strange. Let's see. There we go. Okay, so d dt. Okay, so tangent derivative is going to be secant squared theta d theta dt. And we're going to do a quotient rule. Don't worry, because remember, it's going to look really messy at first, but we have like everything to plug in. Okay, it works out really, I promise, it works out nicely. So low d high, take high d low, right? Cross the line, square the low. Right? Everything on the right side, we have all those values. So it's just going to be a matter of plugging that in. Yeah, so we get 4 times negative 2 minus 3 times 3 over 4 squared. So we said, yeah, negative 17 over 16.
She's getting better.
Okay, now secant, let's look at this. Secant of theta would be 1 over cosine theta, right? Well, when h is, what was h? 3? And this was 4? Okay. And this was 5.
6 over 5.
No. I just mean like, this was a 3, 4, 5 triangle, right? Secant is 1 over cosine. So cosine would be adjacent over hypotenuse. So this would be 5 over 4. So right, this would be 5 over 4. So then if I square this, 25 over 16. So you don't need to like plug anything into the calculator. There's no.
So then would you want to?
Okay. And now I want to isolate d theta dt. So I'm going to multiply by 16 over 25. So negative 17 over 25. And these are in radians. Yeah, we're definitely going to need another day for this lesson, for sure. It's usually going to be a 2-day. Yeah. There is a lot more, because this is where it all comes down to, like, the word problems. It's fine, Yali. It's fine. It'll be fine.
I don't really understand.
Yeah, and there's the word
Wait, can you go
problems.
faster?
Oh, sure.
I think this is a lot of reading.
So don't read it then. Okay.
I don't know how to read.
If it's a lot of reading for a math class, then don't read.
To be fair,
You need a break?
to be honest, it's
Okay,
not really
you
that
want like a
fast.
quick stretch break?
Yeah.
We're filming this.
Don't worry, it's just for Madeline.
We can do like an
I know,
like
she's
a
supposed to be,
exercise.
she just landed.
Did you get notified
Yeah.
by like 360?
Life 360.
My
There
parents
she
like
is.
stuck me at LAX.
LAX. Okay.
My parents like watch me like they monitor my speed when I'm driving.
It's still
Yeah, but it's still
international.
It was really
I
funny
know
the
that.
other day.
They're like, why are you going 55 miles? Like, I'm on the highway.
Oh,
Yeah,
she's on the second
Okay, let's do one more, and then we'll call it a day. All right.
That's fair.
Okay, that's fair. All right, we have a hot air balloon is rising.
So I kind of walked in when you were closing. The test is after Thanksgiving.
Okay.
Oh, I thought the one that's supposed to be tomorrow.
No, there's no quiz tomorrow.
That's on Thursday.
That'll be on Thursday.
So it's on Thursday.
Wait, this Thursday?
Is there class tomorrow?
Yeah.
Yeah.
So class tomorrow, we finish this lesson Wednesday review or no class?
We don't have class.
Oh.
What's it look like? There's like a basket here. Okay, I don't know.
Seems like a big issue.
Okay, you're gonna be fine. Let's not worry about it.
Can I
Let's
see?
do this balloon problem. Okay, a hot air balloon is rising straight up from a level field. Okay, there's my hot air balloon. Oh, and this is my person here. Okay, I can draw stick figures, and that's about it. Okay, so a rangefinder. Anybody know what a rangefinder is? It like
Finds the range.
finds the range. So, like, if you're playing golf, you have a rangefinder to see how far you have to. No. Okay,
Sorry, I don't really.
it's a thing that finds distance. It's exactly what it sounds like.
It finds
So
the
this is 500 feet away. Here. Okay, so here's your liftoff point. It's going straight up. At the moment, the rangefinder's elevation is pi over 4. The angle, so this angle here is increasing at the rate of 0.14 radians per minute. So that means d theta dt is 0.14 radians per minute. And what do we want to find? How fast is the balloon rising? Okay, we need another variable. Want to use h again? That's fine. Okay, so when we say that, we want to know what dh dt is. All right. 500 is constant in this case. So the person is standing over here and the balloon is going straight up. So you'll notice I didn't put any arrows here. This is staying constant. The person's not moving towards the balloon or away.
We have data, right?
Exactly. Okay, so but it's going up. We want to take a snapshot of what happens exactly at 45 degrees or pi over 4. So we can't plug that in because that's not constant. We'll plug it in at the end. Okay, what's the relationship between theta, h, and 500? We could use tangent again.
Isn't H just going to be 500? It's 45 degrees.
Opposite over. No. 500 is the adjacent side.
Yeah, but I thought if it's 45 degrees, then both sides will equal.
Okay, but we can't plug 45 degrees in until we've done the derivative. Because 45 is, this angle is changing at 0.14 radians per minute. So it's getting bigger and bigger because the balloon is going up. So we want to take a snapshot of what happens exactly at 45 degrees. So so we can't plug any, the only thing that we can plug in is the 500. Which, what are we going to do? Okay, dd.
How do you do?
I'm going to rewrite this as 1/500 times h, just so you can see it as a coefficient.
How do you do?
Okay, so the derivative of tangent is secant squared times theta times d theta dt equals 1/500 dh dt. Oh, so we have all this information now. Theta is pi over 4. So secant of pi over 4 squared times 0.14 equals 1/500. Remember, dh dt is what we're looking for. Okay. What's cosine of pi over 4?
Root 2 over 2.
Or 1 over root 2? So take the reciprocal.
Oh,
So root 2 over 1 squared is 2.
So it'll be 0.28.
And then we want to multiply that by? And that'll be 140 feet per minute.
Probably better.